All right, well, welcome. This is Fred Schenkelberg, and today we're talking a little bit about accelerated life testing or accelerated life test. I'm never really sure which way that acronym is supposed to be said, and I've seen it a number of different ways. But the idea is that sometimes we just want to get an estimate of how long something will last. Will this product last long enough? Or just in general, if we're buying, say, a power supply from a vendor, how long will it last? Will it last long enough for our purposes? Will we get our value out of it? And then in a product development process or in a factory setting, we often want to know, is it good enough? Is it good enough to ship? Is it good enough to install? Is it worth this price? Is it going to meet our customers' expectations? Is it going to meet our expectations? We're generally interested in, will it survive over some duration with a high enough probability? Now, one of my first introduction, and some of you may be familiar with it, is to reliability engineering. Is my boss walked into my office one day. I was a research R&D engineer in a factory, and we made heating cables. And he showed me a new prototype one of the other teams was working on, and he said, we want you to figure out, will this survive 20 years in its application? And if not, what percentage will likely fail within that 20 years? And so he was pretty clear what he was looking for. And it was basically the question, is it reliable enough? Well, at that time, I thought I had to wait 20 years to go figure out whether it would last 20 years or not. I had no idea you could accelerate things. And so kind of jumped into the deep end of the accelerated life testing and sorted that out and figured out a way to accelerate that particular failure mechanisms involved with that product. But the question that the design team and the customer wanted answered was, is it good enough? And so it's a pretty basic question, although it often is connected to this duration, which we don't have the luxury of waiting that long to find out. And so that's what makes accelerated life testing such a fascinating topic and why I like it so much. Now, the other way we maybe run into this is doing a comparison. We have two suppliers providing, say, power supplies. I'll pick on power supplies today. And we want to know which one's going to last, give us a better performance, have fewer field failures over time. Yeah, I guess I even had a failure in my failures. So sorry about that, Sean. And so we're just doing a comparison. And we're looking at a way for some duration of time or number of cycles or something like that, and which one is going to have more failures over that time frame that we're interested in. And it's another way we could use accelerated life testing. We're not necessarily looking for how reliable is it over, say, 20 years, but which one has a higher failure rate over 20 years. Now, obviously, those are very similar questions. And yes, William, the slides are going to be available. I'll have them near the end of the session when I bring back up the download file, but you can also find them at reliability.fm underneath the Ascendo Reliability webinar series. And later today, probably tomorrow, I'll have the recording posted and the slides and everything else posted up there. So you should be able to find them there. And if I remember, I'll actually do some spell checking and get that corrected. So here's a basic question. And you can type it in if you'd like, or just yes or no, or how do you know? But when will your product fail? Now, as you think about that and find the chat window and answer this question, this simple quick poll basically. Some years ago, I was in a Best Buy. It's a big box store for electronics products, and I was working at Hewlett Packard at the time on inkjet printers, and I was curious because I was going through the store and I took a look at where the printers that we made were being sold, which was kind of cool. And I was just browsing around, and a woman asked one of the store clerks, one of the guys on the floor there, to help her pick out a printer. And he was all ready with different features and asked her what she wanted to do with it. And she goes, no, 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 no. I want this kind of HP printer right here. There's 5 boxes, and I want to know which of those 5 boxes are not going to fail over the next 2 years. So at that point, I was really interested in how he was going to answer that question. And his basic answer was, well, they're all really robust. They're really good. We rarely, if ever, see these come back. You'll be fine. Pick any of the 5. And she didn't seem terribly happy with that. She said, now everything has a failure rate. I want the one with the lowest one. And so there was a bit of a dilemma there because, as you know, of manufacturing anything, there's a lot of uncertainty. We just don't know which particular one is going to fail or which one's not going to. Right? Now, I'm going to go back to some of your questions. And sometimes the customer spec, if it's out of the specifications, we know that it has failed. But how do you know when it will fail? How do you estimate that? I mean, you can measure it in the field if your customer reports it to you. Some products just get thrown away. Some products have so much noise as to when they get failed or reported as failures. Sometimes, and Richard, you've listed a bunch of tools there of ways that we can go about doing it. So it's a way to do that. But it's one of those fundamental questions that at first we want to know, are we on target to make our objectives, the goals that we've set out? Is it reliable enough? And then later, are we meeting our target? Are we achieving our requirements, our specifications, or expectations? And so this question of why we do ALT is pretty obvious to me anyway. The downside is it's really, really expensive. So there's a number of different ways to go about doing accelerated life testing. And we'll talk about a few of the basic ways to do it, and then I have a couple more advanced techniques that I want to mention. And then we'll round this short presentation out with some of the gotchas, some of the things to consider as you go into doing accelerated testing. Now, one of the basic ones, one of the simplest ones by far, is just run the product more often. Now, of course, this works if it's something that's not used 24/7, if it's not used all the time. So on this alarm clock, for example, there's a number of features that work all the time, right? The hands are driven by definition 24/7. They run consistently as long as it's powered up and so on. And it's got some spring force in it. And this is probably an older clock, so it probably has a wind up on the back. Or if it's a door hinge on a vehicle. Now the door hinge is in a fixed closed position most of the time. And you think about how often you get into your car, maybe you're running errands or back and forth to work. It's on the order of 5 to 10 cycles, which should always be an even number, I suppose. You open it, then you close it. But let's say it's on the order of 10 cycles a day. And so there's plenty of extra time there that you can open and close that door just more often than it is in a normal basis. Now, the hard part here is well, how often do people typically open and close a door, right? My car, since I work at home, has been sitting in my driveway all week. I haven't gone anywhere. My wife drove the last time we went out for errands, and the car door in my car hasn't been used at all this week. Whereas a taxi up in San Francisco has probably had its car door open and closed dozens, if not hundreds of times in the last day. And so there's variability there. And so understanding your market, understanding the use conditions is something that we need to know anyway, becomes much more important when we're trying to understand how to interpret a test. Now, some years ago, I ran into a test, and I got another question for you here. Looking at this alarm clock and a basic mechanical clock, uh, what element of this should we use for that we could use this time compression style testing? We could exercise it more often. Now, um, some years ago, I ran into a game controller manufacturer that was testing the buttons. There's, I don't know, 20 buttons on this game button controller, and they had a little pneumatic hammer that would punch these buttons over and over again. And they wanted to test them for 1 million cycles. And one of the buttons was a sync button, which basically you do once with a game system, and maybe you do it every couple of months if necessary. If you lose the sync, if after say a software update, if or something like that. But they wanted to test that button for 1 million cycles. And I said, why? It takes you 6 weeks to do this. You don't get any failures. You don't have enough time or space to run enough samples. And the button's only used 20 times in its lifetime. Why do you need 1 million cycles? And he says, well, that's the spec. All right, well, is that really meaningful? Does that really relate to anything? Now, the trigger button, the fire button, was used way more often. But even that button, when we went off and measured it, we had ways to go measure these things. We had game players and pros and all walks of life of these gamers were coming in and testing software. And we measured and counted how many times they pushed different buttons. And it would be on an annual basis with some assumptions about how often they would be pushing the various buttons, and this one trigger button was pretty frequent. It was in the tens of thousands, if maybe 100,000 times, if they were pretty much full-time gaming. And so we were testing to 10 times the maximum cycles that we would typically see. And so the ability to translate that is really connected to, well, how often is something used? And I've seen a couple of different pieces come across in the chat window here is, yeah, the alarm, for example, the trigger for the alarm system, now the spring that moves the hands, that's probably running 24/7, right? It's always activated. It might have different forces on it depending on the wind, the state of how much wind is in it. But whether it's truck doors or it's the alarm feature or the turn the alarm on or off, the mechanism to set the time, a lot of those things could be used just more often, just much easier. Yeah. Now, Richard, some of the environmental inputs, temperature, humidity, and so on, we can accelerate those by elevating the temperature, elevating humidity, for example. But is that just using it more often? Is this use of time compression? And I'm going to talk about where we use that approach in a little bit more. Yeah, but it's not everything about this clock is like the metal finish in oxidation, just rusting, for example. We could accelerate that by increasing the amount of oxygen, the moisture, other things involved with it. But it is already subject to that stress all the time. And so just putting it in the environment more often doesn't make sense because it already is always in the environment. Now, if it was something kept in a nitrogen bath to prevent corrosion in its normal use, if we put it in ambient air, that would accelerate it in some fashion, but not necessarily what I mean by this time compression. It's a little bit different. It's a little bit different. So the other idea here, which I think what you're alluding to here, Richard, is if we know that there's a relationship, that we have done some experimental work, we know that the oxidation of the finish is it will last 30 or 40 years, and are able to accelerate that by temperature and humidity, and we create a relationship to our previous work. It might not be a full out physics of failure model. It might be strictly empirical. It might be just our past history that we've known it's done well. For example, I ran into a team that did drop testing for their handheld device, and they found that if they raised the specification for the drop test more often at higher heights and higher had to survive, it forced the design team to make a more robust product. It also related to how long it lasted in the field. Now, there's lots of variability about how things get dropped. And what they found, though, was that they were able to correlate the height and frequency of drops in their testing, their criteria for in-house testing, to the number of failures they saw in the field. And they did that through a number of steps of, well, they tested at a 3-foot drop 10 times, and they got all kinds of failures back from the field when their product just met that requirement. So they doubled it. They said, we're going to go 6 feet and 20 drops. And the designers pitched a fit, they hewed and cried and all those problems, but they designed a more robust product that met that specification. And the field failures went down. And so if I can find some relationship between stress to life, and we can leverage that to run a single point test. And the 8585, way back when, was used to evaluate this newfangled enclosure for electronics. It used to be in metal cans all the time. Motorola moved to a PEM, a plastic enclosure. Basically, they formed epoxy over the active device and the leads coming out of the package. They had a problem with its sealing. And if the overmolding wasn't sealed properly to the frame, it was a path for contaminants to get into the active element and cause corrosion and make it fail. So they did a whole bunch of characterization work, and they found that a way to do a molding such that it would last the 10 years that they wanted. And then they shortened that test by increasing temperature and humidity. And they found that if they had 168 hours, or I think it was 1,000 hours originally, at 8585, that it met their internal criteria for that particular epoxy, that particular frames and systems and so on. And so they had built up the experience and then knew that this was a meaningful cutoff for them, and they designed a test to do that. So these are, don't just do 8585, think you'll get 10 years. It really depends on your product and what's failing and so on. Yeah. So I'm seeing a bunch of comments here. Let me catch up with that a little bit. Yeah, the freeze-thaw cycles. Yeah, that's a tough one, especially, and aircraft see this, right? Exterior elements of aircraft that go up to 30 to 40,000 feet, they're seeing minus 40 degrees C, and then on the tarmac, they're seeing, 30 C or higher in some parts of the world. Yeah, there's all kinds of ways to go about doing these testing, right? And even though whether it's compressing the time or using an existing model, you should be seeing that it's really related to what's the failure mechanism, and can we translate that from the test conditions to the use conditions? We'll certainly come back to that. All right, so I'm going to quickly mention that, like the finish on here, if we knew the oxidation rate, the chemical process that would degrade the finish on this or rust it, the Arrhenius equation, for example, or if we just developed it over time, say the abrasion process of handling, that we could probably create a test that would check its abrasion resistance to say it was suitable or not. Now, a lot of international standards are based on this kind of gut feel and engineering knowledge about, say, abrasion testing or suitability versus different chemicals, for example. Your mileage may change. as we continue to develop new materials, new assembly process, everything else, the old standards may or may not really apply. And so in this style of testing, if you approaching it with some fixed test with an assumed model, we do take quite a bit of risk. So it's something to be aware of. Now, closely related, and I mentioned it briefly, was the Arrhenius rate equation is an example of using an acceleration model. The Coughlin-Manson equation for metal fatigue. There's a bunch of different physics of failure type models dealing with whether it's a chemical process or a wear process or an abrasion process or electromigration process. There's lots and lots of different models out there in the literature and in our textbooks that allow us then to pick a model off the shelf, basically, adopt it to our particular circumstance, the Arrhenius rate equation being you have to get the right activation energy, for example. And these models tend to focus on a single failure mechanism. And so, Rupesh, the acceptance criteria is related to this acceleration model, the ability to translate the test conditions to the use conditions. So even in the previous two scenarios, let's say it's just a car door, right? And let's say I'm assuming this car door is going to see 10,000 cycles in the lifetime that we're interested in. And we run a test, and we find that less than 1% of the car doors are going to fail at 10,000 cycles. That's all well and good. If we find out that the car is being used in a different way than we expected, and it's only used 5,000 cycles, if the test is done correctly and we have a good model, we can interpret that change in the use conditions to a different probability of success. Or vice versa, if it doubles the amount of cycles, we can do that. One of the worst style of tests is inexpensive, is called a success test. We run a number of doors, 10,000 cycles, and if they all pass, we say it's good. It's very convenient to do that. It also minimizes the amount of information we learn, right? So I much prefer run it to failure. It lets you verify that you're getting the failure mechanisms that you expect, that the test is actively working on your system to accelerate what you think it's accelerating. You can verify your model parameters. You can do a bunch of other things. But with every test, it's connected to how it's used and what's your acceleration model and how well is that known and understood. Then you can set a criteria it's pass, fail, or not. Generally, we want to know, is it good enough, right? Or will it last long enough? But even that question has a criteria. Is a 1% failure rate at 10 years sufficient? Or if we have a 10% failure rate in 10 years, is that good enough? And so some of these are not engineering decisions, they're business decisions and customer requirements related. Right? So Arrhenius works for acceleration. If there's plastic parts and there's a creep of that plastic that may change its fittings, that's a factor in this. There's the corrosion. So let's say it's a battery operated one, corrosion on the leads, for example. There might be electromigration problems, although unlikely given the size of the simplicity of the electronics. There could be drop problems with this. And which kind of tests would you do for that? You know, how would you evaluate that for its durability over, say, 25 drops in its lifetime? Thinking through which of these models would work really starts with, well, what's the failure mechanism? How are we going to evaluate it? Yeah, and Rupesh, yeah, sometimes we do have to modify or define our test process to answer the question that's in front of us. That's pretty standard. It's pretty common practice. When you have the capability to create a characterization, to vet out a time to failure distribution, you can answer more questions in going into the future. And you can do more more with that information. If you do the bare minimum, you often then are limited at how you can reinterpret or reevaluate that same information, that same result. It almost always, though, deals with are we accelerating the failure mechanisms we're interested in? Now, this question I have on the screen is, it's not a rhetorical question, is if you're doing a high temperature soak, you're just going to put it in an 85 degrees Celsius oven and high temperature. Let's say it's a oxidation process, and we're going to use the acceleration or the Arrhenius equation to do our acceleration factor. By moving it from ambient into the chamber, we're doing a thermal, a change in temperature. When we bring it back out, we now have a thermal cycle. If your product is very susceptible to failure due to thermal cycling, you may get failures related to thermal cycling on that one, or small number of cycles. The oxygen in the air in a thermal cycling test is acting on your product. If it's an electrical product, the current flowing through the circuits is causing damage. The handling is causing damage. The inserting plugs and unplugging things is causing damage. All of the thousands of ways that your product can fail are simultaneously being active or are active. Some are being accelerated more than others. Now, oftentimes we focus on a particular element of a product in order to isolate to a particular material or a particular assembly in order to isolate the failure mechanism. Some years ago, a friend of mine was doing a whole extensive set of accelerated tests for an integrated circuit, a custom ASIC that they had. And he was complaining that the memory modules kept failing and basically shorting out his test, and he was not getting results quick enough on the part he was interested in. Now, memory and ASICs are similar technology, right? They're both silicon devices. And I said, aren't you worried about the memory failing? I mean, you're accelerating it at about the same rate that your custom ASIC is being accelerated, and you're getting many more failures in memory than you are in the ASICs. And he's like, well, that's not my job. I'm working on the ASIC. Somebody else has to worry about the memory. Then we talked about, well, how about actually collecting the data there and finding out what's really going on? Is somebody else really working on it? But keep in mind that when we accelerate a whole product, lots of different things are happening with whatever force we're putting on it. And sometimes we have to isolate our product or the piece of the product we're interested in order to only get failures in that area. Other times it's the whole product, and multiple things could cause failures. It just complicates how we interpret it, how we can evaluate the results. Now, a couple of the fancier ways to do accelerated life testing is one's called a step stress model. Now, you may be familiar with that term from HALT, highly accelerated life testing, which I talked about last month. It works great when you have a model that is related to the stress at different levels. And so if I'm at 30 degrees C and I have an acceleration factor that's, say, only 2x, and I run it for 6 hours, I accumulate 12 hours of equivalent damage, or of usage time, of real time, basically, in my accelerated model. If I increase the temperature to 65 C, I might be at 100x the acceleration factor, and in 8 hours now I get 800 equivalent hours. I can accelerate it much faster. So instead of holding it at a steady temperature and just waiting until you get results, you can step up in stresses. Now, the real caveat here is that the type of failure mechanism is the same at lower stresses as at higher stresses. This is true in most of the accelerated testing models that we use. or we assume it's true. But in step stress, it's vitally true. And it works really, really well when you have accumulated damage situations, right? So it gets a little bit of damage at low stress and it gets a little bit more damage at higher stresses and so on. And it allows us usually to go much faster. It's really contingent on having a really good model, though, not too many unknowns or uncertainties there. Thanks for joining us, William. And hopefully you can find the recording later, now that he's already gone. Sorry about that. Um, so let's say we're going to test this clock. It's a fancy looking clock, and we're interested in drop testing it. Could we use a step stress approach to drop testing? What would be the questions we would need to answer in order to use the step stress on a system like this? Oh, and Ropesh, I see your question about applications, computer programs. Sure, and I've seen them on, especially on like communication software that's routing calls and doing all kinds of stuff. Is they'll do a stress test by the amount of calls to this software package, and the frequency of use. If it's supposed to route 1 call per second, but we ask it to run 100 calls per second, can it still do it? And oftentimes it shakes out mechanisms in or bugs in software by just using it more often. Oftentimes in software testing, it's just the amount of cycles we get to run it, how often we run it, how many branches we get exercised. And it just takes time. So doing it faster starts to stress the system. Another is to use higher clock speeds, run the software at higher rates. And it shows weaknesses in software. And those are just two that come to mind immediately. Yeah, vibration is one way we could go at this clock, right? If we're not interested in the shock damage of it dropping, but just say vibration damage to it, and say the accuracy of the clock mechanism. If it's on a wall that say backs up to an elevator and it gets a bunch of elevation or a vibration or stairs or something like that, if that was critical to our functionality of the system, we may be able to devise a step stress. Now the key is we got to have a model that relates the vibration accumulated damage at different levels of vibration, different powers of it. So a number of different ways to go at that. One of my favorites by far is you're going to run an accelerated test, and we don't really have an existing model that fits what we're going to do. We don't know the activation energy for an Arrhenius model if it's a chemical process, for example. And so we need to determine that ourselves. Let me see if I can get my pen going here. And one of the ways that we can at different points in time, what we're interested in developing is a relationship. And for whatever reason, my pen really does not like doing curves, but this is supposed to be stress. So this is a low stress and a high stress. And being a statistician, I always like having 3 points if I'm going to create a line. So let's do a medium stress. And so at low stress, we run a test and we run some samples until we get some failures, and we estimate its distributions. And it might be a Weibull distribution if we're fortunate, right? And we have this time to failure distribution around how often, how many are going to fail at some point in time in the future. And we may be plotting the characteristic life on our plot. And then at medium time, or medium stress, we get more failures. And at high stress, we get failures pretty quickly. And what we're getting is a relationship between stress and time. So the higher the stress, the less time it takes to fail. Plus, we're capturing the distribution of time to failure for each of these stresses. So what we're plotting is essentially a surface that's relating that if we were interested in the first percentile of failures, it would be on this early tail of when failures would occur, or the characteristic life, or whatever probability that we're interested in. And so if we want to know how many are going to fail at some point in the future, we just take this curve, this relationship, this line, right? This line, and project it out until we get to a point in time that's in our future that we're interested in. And then we have the distribution related to that. And so what we're doing is we're creating a relationship between time and the stress that we're applying. Now, if it's a single stress like temperature or vibration or drop height or whatever, it's a pretty simple equation. It's just a line. If you're doing multiple stresses, this becomes a multi-dimensional surface, or becomes much more complicated, but you need more samples and so on. But in doing this kind of thing is if I don't know the activation energy, I can solve for the activation energy, which gives me basically this slope. And it'd probably be on a log-log scale. But the acceleration factor is based on this basic concept, is that the higher the stress, generally, right? If you're going cold temperature, it's more stress, the colder it gets, the lower you go, is related to time. And it's time to failure is what we're focusing on. In some cases, we just don't have the knowledge as to what this relationship is. We may have Kaufman-Manson or Arrhenius rate equation as a starting point, but we don't really know. We don't have the parameters we need to fit it correctly. So running multiple stresses allows us then to evaluate and find those parameters. Now, of course, the more samples you run, the more extensive the test, the more stresses you run, the more accurate this can be. Yet it is quite possible to do this with thermal cycling, with high temperature, with humidity, thermal cycling, with high vibration, a variety of different stresses, in order to create your own model to understand how it's going. Now, understanding the failure mechanism and understanding the physics and chemistry of what's going on certainly helps, right? And now, Simon, you bring up a good question here. One of the assumptions I'm making here, and it's one of the tests in creating these models, is that the distribution, the shape and scale parameter at each of these different stress levels is the same, right? The characteristic life changes, but the shape parameter stays the same. So if I'm doing, say, thermal cycling, which is one that I did some years ago, the Weibull distribution at each stress of different rates of thermal cycling was a beta of 2, or very, very close to 2. And so what you'll see is a graph that is, say, a Weibull plot, cumulative distribution function. And of course, I'm going to try to write CDF. So this is the probability of failure. It's 0.01 to I'm going to say 0.9. Come on. And this is time. And it's on a log scales. And so at very high stresses, I get failures pretty quick. At medium stresses, my Weibull plot shifted over to the right a little bit because it just takes longer at lower stress levels to get failures. And then let's say this is my use condition, which I'm estimating. And so I'm making the assumption that the slope of each one of these things, the beta value in a Weibull distribution, is the same. And so by running multiple stress levels, I can test that. I can determine whether they're close enough to being the same that we can make that assumption. Now, when they're different, Simon, your question brings up the point, is that if I have different slopes on say a Weibull distribution on multiple stresses, it indicates that there's a different failure mechanism at play. There's something else going on that's different at different stress levels. There's some other element that we need to account for in the model. And so it could be all kinds of different criteria that are involved, but it's one of those assumptions you need to check if you're using this kind of a simple model for multiple stresses. Yeah, and you can get all kinds of different. Supersmith does this. Alta from Reliasoft does it, and others do it. R does it. R software, which is free. There's a variety of ways to do this. It's basic regression analysis, but it's using um, uh, multiple stress levels versus your time to failure distribution. So it's a little more complicated than what we were looking at earlier. Okay, this just create your own model type testing. I mean, this could be a whole week course in and of itself, which could be fun. I want to leave you though with one key thing here. And this is the 421 guideline. Has anybody heard of that? So if I'm running multiple stresses, the lowest stress is closest to my use conditions and takes the longest to get failures. And so if I put more samples at the lower stress, it increases the chance that at least one of those samples is going to create a failure, or preferably a bunch of them will have failures. And I don't really need to wait till they all fail. I just need some to fail. At the highest stress, it's very likely all of my samples are going to fail within the time period I'm interested in, or have time in the chambers. So I can use fewer samples because I'm going to get more failures. And so the idea is the ratio of samples to stress levels is you put 4 times as many at the lowest stress, 2 times as many is in the medium stress, and to what you put in the highest stress. And this improves your ability to project to use conditions because you're waiting at the lower stresses, and 2, actually get failures that improve the ability of your model to provide you an accurate estimate or accurate model. So it's a 421. It's not quite optimal depending on your circumstance. It's a good guideline to getting started doing multiple stress levels. Of course, you need lots of samples. If just 7 samples is not going to cut it. I've only once had enough samples that I was actually happy with the number of samples I had, and that was measuring a device that only cost about a fraction of a cent each, and I had thousands of samples. And so it was actually more of a problem with how do we test all the samples than to actually run the test out. One more type of accelerated testing is degradation. It's when something erodes or fades with time. And I can accelerate the rate of degradation at different times. So this was what I did initially. This is that heating cable accelerated test I did as my first foray into reliability engineering. My first is the heating cable degraded its ability to produce heat through an oxidation process. And so it over time, it lost its ability to produce heat with the same amount of power applied to it. And so we could measure that. So we put heating cables into a chamber and pull them out periodically and measure it. And we could measure the degradation. LEDs do this. They fade in light intensity with time. All kinds of different devices do this. Things that wear, like a brake pad on a bicycle, for example. Every time you apply the brakes with a fixed amount of force, you can pretty much predict how much wear occurs, right? But as the geometry of the brake pad changes and the angle of attack, as it wears, it's got a different throw and that changes the amount of force. There's a lot of variability in this. But if I put brake pads of different makes and compositions and designs on different bicycles, and we go for a ride every lunchtime and then carefully measure the amount of wear. We could do repeat measurements of these things and measure the rate of wear under a variety of different conditions. Yeah. And so and Mark, the Waybays, anytime you're making one of these assumptions, you have to really understand your failure mechanism and the understanding of it. Now, on a brake pad, let's say I'm using a new additive, and it's supposed to change the wear characteristics of that. With the degradation test, I don't have to wait for failures. I'm measuring the decay or the wear rate as we go. So every week I make a measurement and I track the changes that it occurs. And so it helps us then create a degradation model that lets us forecast the rate of decay to the point we call it a failure. And then we've got time to failure data. We can use that for the further analysis. Now, not all accelerated testing works out well. And there's lots of ways that we can get it wrong. Ideally, well, I guess it's not even ideally. Actually, our customers are evaluating our products over time. They're using it in use conditions, and when there's a failure, many times they report it back to us, especially if there's under warranty or the failure occurs before they expected it to. They may complain about it. Every time we step away from the use conditions by increasing temperature, increasing frequency of use, or whatever we do to accelerate it, we get the benefit of getting to results sooner, which is the accelerated part, right? Yet we're making the assumption that the behavior of our product at the higher stress levels will be the same as at low stress conditions. Now, that's almost never true. And so the closer we are to use conditions, the less important that assumption is. If we take our product that operates at 25C and we put it in a 500C oven, and it doesn't melt, let's say that we don't do any phase changes, the dimensions of our system is going to change. That may affect how it behaves in its failure mechanism. And it adds another wrinkle to our ability to interpret it. Right? So there's all kinds of different phenomena that occur, not just the one we want to occur when we use accelerated conditions. And so thinking through that and minimizing using the least amount of acceleration possible to get to your answer is prudent. It avoids a lot of complications. Sure, I'd love to accelerate it in an hour and get results in an hour. Yet, if those results are meaningless compared to because it's a different failure mechanisms or the interactions of different vectors of stress just don't translate to use conditions. You can screw it up real quick by over accelerating is basically what I'm saying. Now keep in mind too that sometimes like a seal, for example, if I just put pressure in a vessel and try to detect a seal failure, if it's brand new seal and it's newly assembled, it will probably hold 2x or 20x the amount of force or pressure that we would expect to see in use, and it won't fail. Yet, if it's an O-ring, a plastic O-ring, for example, a rubber O-ring, it may need to age. It may need to oxidize a little bit. And that just takes time. So putting it at a high temperature, putting it under stress, if it sees mechanical changes in stress levels, if it's mechanically cycled. All of those things can degrade the ability of the O-ring to function. And so I may need to age it first and then test it for the changes in pressure. And so it's really stepping through and understanding what's the nature of the failure. Button pushing is my favorite. I see so many people use a pneumatic little device that just punches the button over and over for them. And I asked this one medical device, I said, how do your buttons fail? What do you see in failures in the field? And they said it's fingernails and pens. People would use a ballpoint pen to push the button. and it would puncture it and break the seal, and then it would corrode and damage, or the fingernails would scratch the surface. And so why are you pushing the button with a pneumatic hammer that's similar to the soft part of the fingertip and not a fingernail, right? They said, well, we're testing the button according to the standard, and it says activate the button on and off, 10,000 cycles, and proves that it's good, right? Well, that's the mechanical mechanism within the button itself. It's not the enclosure, the housing, that the ballpoint pens and fingernails are problems, right? So keep in mind what is exactly the stress that you need to apply in order to create the failure mechanisms you're interested in. So it's, by and large, if you can keep it in use conditions, the better. The closer you get to that, the easier it is. Yeah, banana boat sunscreen. Yeah. I've heard I don't know why anybody puts them on their body. I've heard that it's like the best finish tester for paints and applications and finishes and like phones and everything else is banana boat sunscreen. There's a handful of perfumes too that are pretty bad. Coca-Cola is no treat either. It can take the paint right off of some stuff if it's not done properly. Bottom line, though, is focus on the failure mechanism, right? And generally for accelerated testing, it's just one at a time. Now, you really do need to do the failure analysis. As you get failures in your accelerated testing, did it fail for the failure mechanism you're interested in, or was it something else? If it was something else, then your testing your analysis gets more complicated because now you've got competing mechanisms at play. You need two different models a lot of times to do that. Finally, it's check your assumptions. Wayne Nelson's book, Accelerated Testing, does a really good job of listing the assumptions that are being made for the different algorithms and models that he writes about in the book. But primarily, is the failure mechanism occurring in a way that I can project it back to use conditions? Is it the same failure mechanism? And is it isolated and understood well enough in the way the product behaves at elevated stresses versus at normal stresses? And so we're making a big leap of faith that this 28x acceleration factor is meaningful. And the more we can do to check those assumptions, and I think it was Simon, I believe, was mentioned as, is the distribution, the shape functions the same? Is one way to check that assumption when you're using multiple stresses. And so the more you know about your failure mechanism, the better you're off you are. Yet it's still prudent to check the assumptions, whether it's a regression assumption that the model you're fitting is appropriate. Oops, I think I just hit a button here. And or is it is it a simple regression assumption you're making, or is it a function about how your customer uses your product, or is it some other phenomena or factor that you need to consider? Trying to talk and hit the slide buttons at the same time, so that you can interpret it correctly. So the bottom line here is that the absolute worst way to do an accelerated test is go out and exercise it kind of randomly, really hard, and if nothing fails, call it good. Now, if you're doing a halt test, you're going to keep going until you get failures. And that's useful, knowing what the failures are. In accelerated life tests, we're trying to answer the question, is it good enough? Is it going to last long enough? Is there a failure rate suitable for our application? And is this one better than the other one in a meaningful way? We do accelerated testing, which is generally a very expensive activity for any development program, in order to answer a question and help our team make a decision. And doing it well allows us to make informed decisions that can avoid making a mistake. If we do an accelerated test and say, yep, this solder joint's good, we can ship it, it'll be good for 5 years, and 3 years later they all failed, we're in pretty bad shape. And so let me pull up the ending slide here, which has the slides available again. And sorry about it, I lost the slide deck there somewhere along the line, so I don't think I had anything earth-shattering at the end of the slide deck. But you can see some of the links for more information and so on. I've been running a whole series on Accendo reliability over the last month on different kinds of accelerated testing. So there's plenty more to read over at the Accendo reliability underneath the CRE preparation notes, series of articles. So there's lots of good stuff coming up.
I'm not finding anything for Avata.
So somehow I got my phone to talk to me there. I'm not sure how that happened. So anyway, yep, sorry about that, Mark. Yeah, I lost my screen there. I had to pull up hit the wrong button on my keyboard as I'm waving my hands around. And so let me see if there's any questions. I saw a bunch of chats going by and it looked like a couple of you were helping each other out there, which is great. But hopefully that was an appropriate, quick overview of accelerated life testing and a few of the gotchas to be careful about. And so what are your questions? See a few people typing here. And I know I'm right up against the end of the hour, so if you've got to go, I appreciate your time joining us today. The recording will be up and will be available as a podcast through iTunes and others through the Accendo Reliability webinar series. And it's also the video recordings along with this kind of view is with live links and stuff will be available for members of Accendo Reliability. And you can find it under reliability.fm, along with 3 other podcasts that are featured on the network. Richard, I have used the Duane model on occasion. It's okay. There's a variety of different models. It depends on what kind of system you have and which one's appropriate. Most of my clients have trouble just collecting the data in a meaningful way in order to use Duane model, and I've seen it used in software applications, the arrivals of bugs, basically, and they used it quite well. Duane and Crow AMSA are related, they're not the same. AMSA model and then Dr. Larry Crow updated it significantly, so he got his name appended to it, is similar to the Duane model in concept as you're looking at reliability growth, but they're not the same. There's subtle differences. The next topic, I believe, is on reliability block diagrams. And I think that's right. You can see the next couple of events are on Accendo reliability underneath live events. I'm also just talked to Adam Barrett. He's going to do a webinar, I believe in July, if I remember, mid-July or late July. And it's going to be kicking off a new program on Accendo reliability. And it's more aimed at reliability management type topics in a discussion forum and ongoing discussion, not just a one-time webinar. Also, I'm talking to people about doing software reliability events, some leadership type events, talking to Perry Perendo about doing some designed experiments type sequence of webinars. Lots of good stuff coming up. Which book was I talking about, Yi? It was, let me type it in here for you. It's Accelerated Testing by Wayne Nelson. It's an older book, Nelson with an N. It's actually kind of expensive. I think it's like $150 or $200. And again, can't spell and type at the same time, I guess. Yeah, it's a great book. And so it looks like you have it. Petri nets are not that common, Mark. I've seen it in high availability type systems and networks. Um, at HP for the very high end, high availability systems that we use for like behind eBay and things like that, we were using PetriNet modeling, and we usually had a dedicated analyst just to manage the modeling. It is it's a very specialized modeling system, uh, pretty useful because it takes care of interactions and dynamic relationships between different parts of your system that a block diagram is just not capable of doing. Vast majority of products do just fine with a block diagram. Yeah, it is tough stuff. To track test progress. Um, no, not. I mean, I've used LabVIEW in the past just because I was able to monitor in situ, and I was able to run uh, tests of different aspects of the product through the chamber wall eventually. But sometimes you have to take it out of the chamber or take it off your test rig and then test functionality in some other more complicated way that you can't devote that equipment to, or it doesn't make sense to evaluate it at the elevated temperatures. Sometimes you run into you're testing your test system more than you're testing your product. So there's a lot of trade-offs there about how to do that. But I've used LabVIEW, and there's a handful of others out there, I'm sure, that can do it. LabVIEW, I mean, it's a programming language, and LabVIEW allowed me to take my thermocouples, essentially, and I had some voltage readings and accelerometers that I could then monitor directly. And then using the changes in those things is able to use that into a model to look at it was a degradation test, to look at where I was. It didn't give me demonstrated reliability. No, it was more of a way to monitor the testing. Was the chamber behaving correctly, and was the product still functional? For example, like checking solder joints for conductivity. Um, if it's cracked through, it might be intermittent. So doing a continuous continuity test and using LabVIEW to monitor it can help you detect those very short opens that occur before it goes hard open and totally fails. Yeah, they're expensive. LabVIEW can be expensive, and I think of it as a programming language. It does take a bit of work to do, but it's a pretty handy tool. All right, so I'm gonna tracks demonstrated reliability. I'm trying to think, Richard. I think Relisoft, and I haven't used it, has a reliability growth module. I don't know how well automated it is to track it for you. I also know of different defect trackers, fracas systems, software systems that had that module that allowed you to essentially do a mean cumulative function of accumulated failures versus time, which is a non-parametric